Jan Vysoký from Czech Technical University, and he will tell us about the graded Lie groups. So please go ahead.
Okay, so thank you very much for an invitation. It's a pleasure to be here, and I will be happy to thank you for coming, and I will be happy to give you some very short introduction to mathematics I'm interested in, and this mathematics is the theory of graded manifolds. So I will briefly tell you what graded manifolds are, and then I will tell you some particular tiny little piece of it, which is called graded Lie groups, and hopefully I will be able to provide you some interesting examples which make this interesting. So I should have found some chalk. Okay, so let me start. So as I promised, first I will give you some introduction to graded manifolds. Second, I will define graded Lie groups. And in the third part, I will give you some examples of graded Lie groups. Okay, so let me start with the graded manifolds. Okay, so what I mean by graded, all the time when I say graded, I mean Z graded. So we usually omit the Z. So sometimes people call supermanifolds graded manifolds, but no, I will be strictly talking about Z graded manifolds. And in essence, what are Z graded manifolds? They are kind of generalization of ordinary manifolds, allowing for functions which depend on Z graded, not strictly commuting variables. So what I mean by that, they allow for Z graded variables. Okay, so let me for a second write them at Z lambda. What I mean by that, I mean that each of those variables has some integer assigned to them, and this integer is called degree of the variable. And variables you use commute according to this degree. So if you interchange them, you either pay a sign or not. So if both of them are of odd degree, you pay a minus sign. If one of them is of even degree, you don't pay any sign. More precisely, so this is just a vague definition. More precisely, but not still completely precisely, you can split the coordinates into two parts. So first, you can consider some degree 0 coordinates. So out of those variables, you single out degree 0 ones, and which we denote by x's, and non-zero degree ones. So you can call them, maybe I sometimes call them purely graded coordinates. And what are now functions on graded manifolds? Of course, not globally, but locally, wherever you have your coordinates of the following form. So each function on your graded manifold is some formal power series summing over some index. I won't go into too much details. And there are some coefficients of those formal power series, and those coefficients are smooth functions of those degree 0 coordinates. And there are formal power series in those non-zero degree coordinates. So this is just a shorthand notation. So what is psi2 p means? So you take psi1 to the power of p1 up to psi and star, some power of pn star. So these p's are actually some n star tuples of non-negative integers, telling you which power you have to take of your size. And of course, if you want to say that this function is of degree of some defined degree f, then these multi-indices have to satisfy something. Otherwise, it's not a function of degree f. So what is the constraint is that something like sum or pm's times degree of p mu, c mu, and there is a sum over mu is precisely this degree of f. So you only allow for such combinations of size such that they combine to the correct degree. So this.
That like that? The absolute sign.
F. Yeah, my very not.
Same one as
this one. Yeah, and also this one. So this basically what you want to do is to have some theory where you can work with such kinds of functions. Of course, you want to make this into algebra, so you have to define, multiplication. So and multiplication is defined using the similar formulas and product of two formal power series, except there are some signs involved because you have to interchange the orders of those size, and basically you imply this rule everywhere you have to, and this gives you some non-trivial signs. But it's kind of, and if the power series is finite, which is also possible, then all the manipulations are just naive manipulations as with finite polynomials in your size. But you have to allow for infinite formal power series for the theory to be consistent. Okay, so these are our local functions, and in fact, what you can show that such functions for sections of some sheaf, so they form a section of sections of a sheaf. I'm intentionally vague. We need to do this sheaf like this, where this is a sequence. So we omit writing here. It's a sequence of non-negative integer, and this nj is basically number of size of degree j. So you calculate how many size of each degree you have, and this gives you some numbers for each j, and you combine those numbers into a sequence. So this is a kind of local model of our theory. And now comes the actual definition of a graded manifold, the precise one. Okay, so a graded manifold of a graded dimension so graded dimension is a sequence of negative integers, is a graded locally ringed space curly M. So we always denote graded manifolds by curly capital Latin letters. And I will explain in a second. Where, or such that. Okay, so what is a graded locally ringed space? So it always consists of a topological space M, because it's a basically topological space together with some sheaf of it. So our topological space M is assumed to be second countable Hausdorff topological space. So this is the first part of the definition, and this C infinity curly M is a sheaf of graded commutative algebras, graded commutative associative algebras on M. And the third thing is that C infinity M as a sheaf is locally isomorphic to this local model sheaf I have defined on the previous board. And in fact, automatically it's a local ring space, meaning that its stalks are local rings. This is automatic from this property. And just a technical detail, we always assume a finite dimensional case. So we assume that some of those nj's is actually finite. So only finitely many of them are non-zero. And this is what is a graded manifold. And this is just a technical definition. So let's establish some basic facts about those. So let's consider this as a list of basic facts. So what is the common name? So sections of C infinity curly M of these sheaves are usually called functions on M. It's curly M. One can show that from this definition, from this local isomorphism to this local model sheaf, it already follows that M, this underlying topological space, is already a smooth manifold. And each function on our graded manifold over some section over some open subset of M has a body, which is denoted as F underline, which is a section, which is a smooth function on this underlying smooth manifold, smooth function on this underlying smooth manifold over U. So basically, there is always an ordinary manifold underlying the graded manifold, and each section of this sheaf, meaning we call it function on curly M, has an associated ordinary function lying under it. It's called body of function, and yeah, and that's it. So how do you define maps of graded manifolds? So graded smooth maps, or just smooth maps, they are denoted simply by like maps, but they are not actually maps. But we use the notation which tends to mimic the classical geometry. So graded smooth maps between two graded manifolds are morphisms of local ring spaces, or graded morphisms of graded local ring spaces. That is, so I will now explain. So each graded smooth map is secretly a pair of two additional maps where this phi underlying It's just a continuous map from M to N from between the underlying topological spaces. And this phi star, which is called pullback map, is a sheaf morphism from the sheaves of structure sheaf of this guy into, not into structure sheaf of this guy, but into its push forward, but basically push forward sheaf of push forward sheaf of functions of this guy, meaning you just have to make them into sheaves over the same topological space. So you make them into sheaf of over N. And this is a morphism of sheaves of algebras. So basically you can use graded smooth maps to pull back functions from the second graded manifolds to the first one. Okay? And then it's obviously, it's not difficult to prove that this makes graded manifolds into category. So you have morphisms, you have objects. So you have category of which I denote as G-man infinity. Of course, ordinary manifolds fall within this category. So ordinary manifolds are subcategory of this category. In fact, full subcategory. Okay, and what is interesting about this category is that this category has finite products. Which will be important for our definition of graded Lie group. In particular, it has a product of no graded manifold, which means that it has terminal object. Terminal object. In fact, what is a terminal object? It's easy. It's a single point manifold, ordinary single point manifold, just one point. Okay, and the last thing about graded manifolds, which we have, which is important again for technical purposes. So at each point on the underlying topological space, there is a tangent space TMM. So to every point of our underlying topological space, there is an associated tangent space, which is a graded vector space, real graded vector space. And what is important, that each graded smooth map from curly n to curly n induces for each point the tangent map, which is just the graded linear map of degree 0 between two tangent spaces. So this goes to tie, and the point is an image of this underlying map of phi of m to curly n. And this is very important because if you have, do you have a question?
Yes, so please.
Okay, and the important thing is that if you have the notion of tangent map, then you can you can speak about local diffeomorphisms, you can speak about emergence, submergence. There is inverse function theorem for graded manifolds, so you can use this to construct diffeomorphisms between graded manifolds. Okay, sure.
Okay, so that's a class of a locally ring space.
Mm-hmm.
What is the biggest motivation to study this class?
The motivation is that this is the viewpoint on manifolds, which allows ordinary manifolds to be interpreted as locally ringed spaces. So it naturally just switch from local ringed spaces to graded local ringed spaces. So that's the first answer. And the second answer why you actually need local ringed spaces is, I didn't tell you that this map, which is only assumed to be continuous, is then automatically smooth. And this is the consequence of the fact that there are local ring spaces. Yeah. Let's
So that's a zero-sum question. In the tell me which round graded the manifold. That's very hard to solve. But then it can solve using this category.
no. Yeah, I have no idea. I don't know.
Yeah, so that's a check try to introduce new object to study.
Okay. Thank you. And so just to give you some example. So the simplest example. Okay, 20 minutes. Just the simplest example. So of course you can consider finite dimensional graded real vector space. And as in the case of ordinary manifolds, you assume kind of you expect that out of that you can somewhat view this canonically as a graded manifold. And this is the same thing. So what is the just note what is a graded vector space in our viewpoint, which we tend to use. It's just a sequence of ordinary vector spaces. So graded vector spaces are just sequences of ordinary vector spaces, and then there is an induced graded manifold which we denote as GR of X, like graded manifold out of X over. And what is the underlying manifold? The underlying manifold is X0. So you take zero component of this graded vector space, and this is your underlying manifold with usual, finite dimensional topology you have on your vector spaces. And and basically how there is a kind of definition. I can give you precise definition of the sheaf. So in fact, how does one thinks about this? So if you have some basis X, in our definition, you always have just homogeneous basis. So you technically take all the bases of X case and kind of mash them together into one big guy, and you call this a basis of X or total basis of X, and then out of it you take its dual basis and to the dual basis you associate those graded coordinate functions. And this is how you think about that. So what is interesting that the graded dimension of GRX is, so this sequence is in fact this kind of peculiar thing. So it's ordered in the opposite way because of this duality, because you start with basis. So there's precisely J dimension of Xj number of those elements, and the dual basis has the opposite degree, right? Because it has to give its degree minus d lambda map. So this kind of interchanges degree. As for the ordinary vector spaces, we usually just write X instead of GRX. So we usually just write X instead of GRX. This is slightly confusing sometimes here because of this dimension interchange, but we still use it often. There are some notes. If you take two graded vector spaces and you have degree 0 graded linear map between them, then you can promote it to a graded smooth mass between the associated graded manifolds. And in fact, you can prove that this GR can be interpreted as a functor from the category of finite dimensional real graded vector spaces into the category of graded manifolds. So it's a nice thing to have. Yeah, and that's it. So this is the short introduction to graded manifolds. So I can now start talking about graded Lie groups. So definition will be very simple, because as I already commented, graded Lie groups, graded manifolds form a category which has finite products. Therefore, we can talk about a group object in our category. So graded Lie group, GLG for short, is a group object in category of graded manifolds. So this is just a short definition. That is, for tuple, capital G, mu, iota, E, where, so I will now decipher what I mean. So this capital G is an object in Gman infinity. So it's just a graded manifold. Second, this mu is the graded smooth map from G times G, G, smooth. Because we have binary products, we know what this G times G is. This iota is a map from G to G, and this is called, of course, multiplication. This guy is called inverse map. And what is the fourth ingredient is this E, and this E is just a map from the terminal object. That's why you need terminal object. So terminal object is a 1-point manifold into G. This is called unit. There is one comment here. It's pretty clear that this is very trivial thing, because it's just a choice of a point in the underlying topological space of this curly G. So this E is actually, it's a point in this non-curly G, which is the underlying manifold of this curly G. And that's not all, of course. There are some axioms. So, but you probably already know, but they kind of mimic the associativity, left unitarity, right unitarity, and inverse axioms you have in groups. So, for example, just an example, very small one. I don't have enough space, but something of this kind. So you have this associator, which is diffeomorphism in the category of graded manifolds. And then you can take mu times identity to get to G times G, then use mu to get to G, or you can take 1 time identity times mu to get to G times G, and then take mu to get to G, and you impose the commutativity of this diagram, and that's associativity axiom for a graded Lie group. Okay, so this is the definition. So this is very straightforward. But there is one hidden kind of semi-issue in this definition. Of course, that graded Lie groups are not graded groups. So kind of naively, what you would like to have is some group with some grading, with the product somewhat preserving this grading. No, graded Lie groups are of completely different kinds.
Graded Lie group is a Check the Lie group of the graded Lie algebra or not?
There is an associated Lie algebra to graded Lie group.
So of course, that's because I was mostly, I think that I have a very good motivation to explain why you need graded Lie algebra to solve the problem in Lie group, yeah, because you consider automorphism and that's a finite order, yeah. Then you define the Lie algebra, graded, so that's a really necessary object to study Lie theory.
Mhm.
And then you begin from the graded Lie algebra. So I consider that the Lie group of the graded Lie algebra. So that is a graded Lie group in your definition, right?
Mhm.
Yes. Yes, yes. So that's from my point of view, maybe that's then you define because that's now how to say curve notion of Lie group, graded Lie group. Because the beginning thing, of course, here also interesting. Everything is how to say, flat case or ideal case, like a Klein theory. Yeah? So it begins from the Lie algebra. You go to group, and you consider from the sheep, yeah, graded sheep, and you ask at the analog of the statistics, and you go to the concept of graded manifold. So that, but you say that's a your definition of graded Lie group is not a graded group because graded group you mean
Because graded group is a set with some additional property. For us, graded Lie group is not a set; it's a sheaf. It's a sheaf. So it's a sheaf of graded commutative associative algebras, and it's not a set. That's the thing.
So can I ask just to clarify, is there a notion of graded group that already exists?
I'm not sure.
Okay, so what would you be comparing to?
To kind of naive, kind of I wanted to point out that kind of it's if you think about graded algebraic structures, you usually think about them as some ordinary algebraic structures which have some degrees on them. So elements of your, or some elements of your ordinary algebraic structures have some degrees, and your operations on your ordinary algebraic objects somewhat preserve this degree. This is what I meant by graded group, right?
Mhm.
Like it's not ordinary group with some additional grading on it, such that your operations have to somewhat be compatible with the grading.
So I don't know if you were planning to go into details on this, but if you would just dig into that a little bit more. So can you? I think if you look at the body of this structure,
It's just
right?
the
It's just an ordinary
I
Lie
wanted
group,
to comment on it. Yes.
right? And do you have like a representation theoretic description of the data that goes into a graded Lie group, like some module that you can interpret as the extension of the multiplication on the graded parts of the action? Okay.
Kind of, I wanted to keep things as straightforward as
Right,
possible.
okay.
So we don't have any well-developed theory
Okay.
because we were still looking for some elementary examples.
Mhm.
So this is not completely developed. There are some notions we have. We have notions of graded Lie group actions. We have notions of graded Lie group representations. As I will tell you now, we have a notion of associated Lie algebra to every graded Lie groups. I think Kotov and Salnikov, they have the other way around. So they can start with graded Lie algebra and give you graded Lie group. They have integration procedure. Yes.
So just my comment would be that would be interesting to kind of collect the group theoretic or representation theoretic information that is encoded in a graded Lie group that you can present without talking about graded manifolds.
Okay.
Okay, just would be interesting.
Okay, so I will now erase my board a bit. So I should give you some examples, right? Of this structure. So some simple example. So you can take graded vector space and you can view the addition on your graded vector space as a graded smooth map from x times x to x. So there is a way how to view the addition you have on your graded vector space as a map from x times x to x, viewed as a graded manifold. And of course, multiplication by -1 can be viewed as a map from x to x. So this comes from map which assigns to each vector a minus vector. And then there is also association of the zero vector, which you can view as a map from singleton manifold to x. So, and the claim is it's not difficult to prove that this is graded Lie group. Okay, so this simply generalizes the fact that if you have a vector space, you can view it as an abelian Lie group, and the same thing works here. Okay, there is a notion, as I already told you, there is a way how to get the Lie algebra out of graded Lie group. So there is a notion of left invariant vector field. Okay, so I didn't tell you what vector fields are, but vector fields on graded manifolds are just the graded derivations of your algebra of functions. So you can define them algebraically, but everything works as expected. So you can take commutators of graded vector fields, graded commutators. Yeah, everything is finite dimensional. Yeah, sure. Okay, so you can take a vector field, so vector field on G. So this is a sheaf of vector fields, sheaf of graded derivations, and there is a open set where they are defined. So I consider globally defined vector field, and I say that it is left invariant if, and you can impose purely algebraic condition. So I will write it like this. So you can take some function on your graded Lie group, and then you can pull it using multiplication to the function on G times G. And this is just a vector field, which kind of vague notion, but it's just a vector field. It's kind of lift of the vector field to the Cartesian product. So it's basically the vector field it's just acting on the second bunch of coordinates you have. And you can define it, in some clever way, but it's basically that. So you can pull it by mu to G times G and act by this vector field. And there's a typo, or there should be a typo. In my notes, there is a typo. Or you can first act by X, this is new function on G, and then pull it back using mu. And if those two operations kind of commute, then you call the field left invariant. This is if your graded Lie group is actually ordinary Lie group, then this is just the notion, the usual notion of left invariant vector field, and they form left invariant vector fields form a Lie subalgebra which is denoted as of the Lie algebra of all vector fields. So by Lie algebra, I mean that I have a graded commutator of vector fields which forms a degree 0 graded Lie algebra, and left invariant vector fields form a Lie subalgebra of this Lie algebra. And in fact, you can then prove that tangent space at the unit of your graded Lie group is isomorphic to this vector space. So this is actually finite dimensional vector space, as in the ordinary case. And this is what you call Lie algebra associated to your Lie group. So there's a straightforward way how to get a Lie algebra, graded Lie algebra out of your Lie group, graded Lie group. In fact, this is a functor. You can prove that this is functor. So we have a Lie functor going from graded Lie groups to graded Lie algebras of degree 0. They are always of degree 0 because they come from the graded commutator, which is of degree 0. So preserve the degrees. Okay. And in this example, of course, the associated.
Before you even define left invariant vector fields, you already have vector fields.
Yes.
And they are a graded vector space.
Yes.
And there's a Lie bracket on them.
Yes.
So they're just all vector fields on the Lie group are already a graded Lie algebra.
Yeah, sure.
And you're singling out a particular sub
Yes.
Lie graded sub Lie algebra.
Exactly.
And that's going to be the tangent space.
Yes.
Okay.
Thank you. Okay. And of course, if you take this example, then because it's just a graded vector space, then the tangent space to the graded vector space can be identified canonically with the graded vector space itself. So this the algebra is just X itself, and the bracket happens to be the 0, 1, trivial 1. So, okay. And now to some more interesting examples. Of course, this is very trivial, so we wanted to have some non-trivial example. And of course, the first Lie group or graded Lie group we would like to have is to be general linear group. To have, okay, just a second, I will erase this. So we are now coming to the third part, examples. And the first canonical example would be, of course, general linear graded Lie group, right? So you would like to find a graded Lie group such that its Lie algebra is algebra of is graded space of all graded linear maps. So you take finite dimensional real graded vector space, arbitrary one. And then you can take something which we know as GLV, but it's a space of, it's just a space of graded linear maps. A is graded linear. Okay, so this is a graded vector space because each graded linear map, especially in our viewpoint, because we only consider homogeneous elements of everything. So we only consider the homogeneous maps, so maps which have well-defined degree. And if by having a degree means that if you look at the degree of the result of A acting on V, it shifts the degree by the degree of the map. So this is what we mean by a map of degree A. It means that it shifts the degree by V. And if you take Lth component of this graded vector space to be set of degree L or vector space of degree L linear maps, altogether this forms a graded vector space. There is a nature Lie bracket on this guy, and this is just a graded commutator. So you can take A composed with B minus -1 to the A, B, being composed of A, and this is in fact well-defined graded Lie algebra on this graded vector space. And we would like to have a graded Lie group which integrates this one. So the graded Lie group such that its graded Lie algebra is precisely this guy. So it's a very natural question. I will only be quite vague with some definitions because it's not that easy. But not that difficult either. I will give you some basic ingredients. And actually the proof that it's a graded Lie group is in the master thesis of my former master student, Rudolf Schmolka. So you can find it there if you wish so. Okay, so what are the ingredients? So first of all, we have to have graded manifold GLV. So what is the graded manifold in question? So first of all, just define a kind of finite set, which is set of all integers such that the kth component of V, the degree k elements of V is non-empty. And this is a finite subset because we assume that V is finite dimensional, real vector space. So this is just a finite subset. And then you notice that the degree 0 part of this graded vector space GLV can be written as a product over this I of ordinary GLs of VKs. Because you can decompose every degree 0 graded linear map by restricting it on VK, and because it doesn't shift the degree, it ends up in VK. Therefore, you can write every element of GLV0 as a sequence of maps labeled by finite set. So it's just finite sequence of those. And you can consider open subset. So this is just a topological space. It's finite dimensional vector space. And you can define open subset, which is a product of big GLs. So you only consider sequences which correspond to maps which are all invertible linear maps from VK to VK. And then GLV is, you take this graded manifold. So again, I'm omitting this GR functor, but you take this graded manifold, GLV, and restrict your sheaf to this open set. Oh, sorry. And this is your graded manifold. So this graded Lie group GLV is just an open, kind of, in a sense, open submanifold of the manifold of all linear maps. So this is, here it is straightforward how to define the manifold itself. Okay. So how do you define multiplication? So this can be done in a clever way here. So you can consider map mu0, which takes the tensor product of two graded linear maps and composes them. And this is mu0 can be viewed as degree 0 linear map from GLV, tensor GLV, and the tensor product is over R to GLV. And this is degree 0 linear. Therefore, it can be It can be viewed as a graded smooth map from this. So this is finite dimensional graded vector space. So this is a graded manifold. Canonically, this is a graded manifold. So you can view this as a smooth map from this guy to this guy. And then you construct, you take the product manifold. So you take the product of those GLVs. And there is it's very easy to construct a canonical graded smooth map from here to here. It's motivated by this usual, there is always this map from V times V to V tensor V, very natural one, taking pair VW to V tensor W. So this is motivated by this map. So it's a graded smooth map, and so you have to write it in some local coordinates, but it's very easy to do. And kind of this map obtained by composing those two, you denote it by mu. And like not mu, precisely because you then define mu to be mu0 composed with alpha, and you restrict yourself to this open subset u times u, and in fact this gives you map from GLV times GLV, and you have to just verify that it actually ends up again in GLV, but there is a machinery to do that, and you can do that, and this is your multiplication. So this is multiplication. So you are almost finished. And the problem is with unit is also easy. It's easy to get the unit, right? Because you just have to point. You know what will happen, right? Because as I already told you, or didn't tell you, but somebody asked, the underlying manifold of every graded Lie group is ordinary Lie group. And your unit has to be the unit of the graded of the underlying Lie group, and the underlying manifold of GLV is a product of GLV case, right? So of course the unit has to be the sequence of units of those GLV case. So the unit map GLV is actually just a choice of the point in the underlying manifold, and it's the sequence of unit maps in your underlying manifold. So this is the unit. And the elephant in the room is the inverse. And the inverse is, sorry, this is E unit. And this is E from the 1-point manifolds to GLV. And the choice of the map from terminal objects is just the choice of the point in the underlying manifold. And the inverse is the elephant in the room because there is no simple formula for it. You have to define it in local coordinates. There is some motivation leading to the final formula. So the motivation is somewhat that you want the transition maps of graded vector bundles to be interpreted as a maps from some graded manifold to GLV, right?
So isn't the formula for the inverse just a Neumann formula for the Neumann series for the inverse? Like integral plus perturbation, and then you have
basically
the infinite series.
Basically it is, but you cannot do it directly. You have to do it like describing how the inverse acts as a pullback on some coordinate functions, and then basically you mimic some, because you take your kind of degree 0 coordinates, do the usual inverse in degree 0 coordinates, and all these non-zero degree coordinates, you can formally invert it by this power series, and it works because they are purely graded. Therefore, those infinite power series are actually not infinite because you can cut it at some degree, and it works. And that's how the inverse is defined. I want to write down the formula, and that's, if you want details, look into the master thesis of Rudolf. Okay, and its Lie algebra is indeed GLV. Okay, I'm almost out of time. Unfortunately, the most interesting example is, so I will be very vague. So the second example is graded orthogonal.
Yeah, how much time do you need to present the example?
Like 10 minutes. Okay, so what is a graded Lie group? A graded orthogonal group. So first you have to define what is a metric on a graded vector space. So you have again a graded vector space, and the metric is just an isomorphism from V to V star of degree L. So you fix the degree. So your metric can have non-zero degree, so it doesn't have to preserve the degrees. You assume to be isomorphism. So, and there is of course some symmetry property which can be written, and you have to give some thought to the signs, but it turns out that the correct signs is something like L plus VV G W, something like this. It's well motivated. This is not coincidence, the sign here. I cannot explain it right now, but there is a kind of good reason why there is this particular sign here. And this is what you call a metric. And it turns out that if you have such a metric, then your space of all graded linear maps decomposes as direct sum of symmetric maps with respect to this metric and skew symmetric maps with respect to this metric. And I'm kind of tentatively denoted as small o VG, right? And what are those guys? Okay, so guys in symmetric satisfy something like this. So if A is in symmetric part, the symmetric map. So if you compose it with G, or first compose it G with transpose of A, so, and there is some sign. And so this is a symmetric, and of course antisymmetric just has additional minus behind the equal sign, and that's it. And of course, you would like to construct what you would call graded orthogonal group. You can now check that this is a Lie subalgebra of this Lie algebra, graded Lie algebra. It's straightforward check that this relation is preserved under graded commutator. And you would like to have a graded Lie group which integrates this graded Lie algebra. And that's possible. So I will be very brief because I'm almost, no, not almost, I'm 2 minutes. But I think it's interesting. Of course, you cannot define it as a set. So in ordinary geometry, you would say, okay, I only consider maps which satisfy some condition. Of course, here you can do that. So you have to approach it in a clever way, or at least I think it's clever. Okay, so you first define map TO, which takes, I will just write the formula for the map. So it kind of composes transpose of A with G inverse and G. And this is in fact defines a map from GLV to GLV of degree 0. You can show this, that this is in fact a map from GLV to GLV of degree 0. And therefore you can view it as a graded smooth maps between those two graded manifolds. And in fact, if you restrict it to U, the open subset U, it ends up again in the open subset U. Therefore you can view it as actually So as a map, smooth map, really smooth map from GLV to GLV. Right? So you can use this map, view it as a map of graded manifolds, restrict it to some open submanifolds, and check that it actually defines a map between those two graded manifolds. And then you define map phi, which is kind of composing using this. I will explain it a bit. I take this composition, which is mapped from GLV to GLV. And what this maps actually kind of classically, so what this map would do if this would be ordinary manifold, this map will take invertible map and take tau of A and multiply it by A. This is what this map would do up if it would be ordinary manifolds. And of course, if there would be ordinary manifolds, there will be no sign, and this will give you G A T G inverse A. And what you would call orthogonal matrix, you will say these are precisely the maps A, which give you identity on V, and this will be orthogonal maps, right? So this is how you classically define orthogonal matrices to be those such that this phi maps them into the identity matrix. And this is how you define your graded, your ordinary orthogonal group as a subset of GLV. And we do the same thing, of course, but we cannot define them as sets, but you can still define inverse images in category of graded manifold. So I will now write a diagram and comment on that. No, sorry. So there is this singleton. Then there is this manifold. I will comment on it. There is GLV. There is this phi, and then there's OVG. Okay, and what is, so first of all, what is this? Because this SymVG is a subspace of GLV, then you can view this as a submanifold of this guy. And then you can restrict yourself to this open set, and you obtain submanifold of big GLV. So this is just a submanifold of this manifold, which is restriction of these to open, basically to invertible maps. So classically, this will be invertible symmetric matrices, but in graded geometry, it's not a set, but it's subgraded manifold. And then you prove that unit kind of factors through this submanifold, so you can view it kind of without ambiguities as a map into this graded manifold. And also the same is true for phi. So phi also doesn't end up in GLV, but it ends up in this submanifold. Therefore, you can view it as a graded map, smooth map form. And then you declare your OVG to be defined by this diagram. So you claim that you declare this diagram to be pullback in your category of graded manifolds. So there's some universal property in play. And then you, of course, have to prove, that's the technical bit, which I won't go into. Then you have to prove all the technical bits, right? So you have to prove, and such a pullback exists if this phi is actually surjective submersion. And this basically means that you can view this as a level set of this map phi over this point E. So if you prove that this is surjective submersion, then this pullback diagram can be completed, and it's unique. It's pullback, so it's unique up to isomorphism. So you have to prove that, and then of course you have to prove that this is actually a Lie subgroup of big GLV. And by doing so, you have to take the multiplication of GLV and prove that if you restrict to this, it ends up again here. And the same for inverse unit, then it's automatically doing what it should. But you have to prove this, and it's not trivial. Like it's quite a long calculation. You have to prove, in fact, that this map tau is anti-homomorphism of GLV to GLV, and this is the only thing you have to prove, in fact, to prove that the multiplication can be restricted to this, and then you can prove that easily that this is a graded Lie group. Its Lie algebra is precisely the kernel of the tangent map to this map at the unit, and this gives you precisely this small OVG effect. So the graded Lie algebra of this guy is this small OVG, and you have your graded orthogonal group for any metric of any degree on any graded vector space. And in fact, you can modify this very easily. You simply put here minus, and this gives you graded symplectic group, right? Because if you put here minus, you have graded symplectic forms on your vector spaces, and you get graded symplectic group. So we have now notion of graded orthogonal group, graded symplectic group for any signatures and everything. So far, we don't have any analog of SLs, right? Because there is no, I don't know if there is any kind of determinant on graded vector spaces. It's probably not. It's not that easy in general, right? As in the supermanifold case, it's the same thing. But we still at least have some non-trivial examples of graded Lie groups we can play with, and hopefully this justifies our definitions and further endeavors with graded Lie theory. Okay, thank you very much for your attention.
Yes.
Yes, I have a question. So that's about the graded manifold. You can match the Z2 CP manifold, right?
Mhm.
Graded. So that you can consider that the Z-graded manifold is the subclass of CP manifold. I mean, that's a final structure.
Yeah, it's not the. Okay, so you are asking whether graded manifolds can be viewed as a special case of Z2 graded manifolds with some extra structures. It's not that easy, right? Because it only works if we consider there is a big problem with graded manifolds. If you work with graded manifolds where you only have degrees of either all positive or all negative, they are called NPU or not NPU. They are n-graded manifolds, like non-negatively graded manifolds or non-positively graded manifolds. Then it's easy because everything in are just polynomials in your graded coordinates. But it turns out that to have some fully working Z-graded manifold theory, you really have to go into formal power series. And if you go into formal power series, then it's not like that graded manifolds are supermanifolds with some extra structure. There are some examples. There is some non-trivial intersection between those two, but it's not the case that all of the graded manifolds are canonically supermanifolds.
Do you have maybe a short catalog of, besides the examples that you gave, of other things that you can show our graded Lie groups?
Okay, as I already told you, there is a notion of representations, actions, and then we can do what we also try to do. There is a fully working theory of principal G bundles over graded Lie groups, where we can do connections, curvatures, and everything. So that's what we have so far in this.
But I mean, specific examples of actual graded Lie groups. So you showed us GL.
Those are those we have so far.
Those are the only ones.
Yes.
So far. Okay.
So far, yeah.
Okay. So maybe just curiosity. you define these orthogonal, greater orthogonal groups for metrics of any degree, this L, little L. Are there any relations between these groups for different Ls?
I think what you can do is there is a procedure in the graded category called degree shifting, where you can take a graded vector space and you can shift the degrees. And I think if you shift the degrees, then your metric, graded metric, becomes I don't know. Does the degree sameness stays the same or not? I'm not sure now. So I don't know. The short answer is I don't know.
So it'd be interesting to investigate.
There is some interesting thing happening, because I'm secretly don't telling you some serious consequence of having degree L metric, because not every graded vector space admits metric of a given degree. There are even graded vector spaces which do not admit any metric at all, right? Because there is a secret problem here, because this graded vector space and this graded vector space have in general different graded dimensions, because kind of the graded dimensions of this one are labeled kind of the other way around. So, and this is isomorphism. So kind of the kth component of this guy and k plus elf component of this guy has to have the same dimension. Otherwise, it's not possible to construct a metric. And this is, of course, not true in general. So, yeah, so there are some serious restrictions on the graded dimensions of V in order to have degree L metric on them. I think some of the examples, in some of the examples, the underlying Lie group is in fact trivial. So in fact, this is kind of, you can construct groups which are kind of purely graded. They have no underlying trivial underlying Lie group, and there is a still non-trivial graded Lie group structure on them. Yeah.
Any other questions? Okay, no questions online as far as I can see. So maybe we can thank Jan again.